Today we are going to talk about something very interesting that you probably cannot find in other online courses because I make it up, okay? So what we are going to do today is trying to connect what we have learned, Bayesian classifiers and also linear regression. Two subjects that doesn't seem to have any relationship at all, okay? I want to draw the connection. I want to show you that indeed they are doing similar things under certain conditions. And I want to convince you that if you understand one, you probably will understand the other. Okay? And when some of your future employers ask you, okay, what is, which method should I use? You have a better way of addressing that kind of question. Okay? So that's the purpose of today's lecture. So where are we? We are in the middle of discussing linear discriminant analysis. We are at the end of the generative models. In this generative model, as I have mentioned multiple times, we are assuming a model behind the data, and we are trying to estimate the model parameters. Once we know the model parameters, we can define the decision boundaries. This is very different from a discriminative approach, which doesn't really require a model. So linear regression belongs to discriminative method. Bayesian approach belongs to the generative method. Okay. However, the two, they are doing the same thing under certain conditions. We want to learn about that today. So here is what we are going to do. There are two parts of the lecture. First of all, we will review the linear regression since it has been a few weeks from then. So we want to look at linear regression again, and we want to see how can this linear regression be used in a classification problem, right? Because linear regression, when you're thinking, is more like a curve fitting problem. How can this be applied to a classification problem? So we want to make that linkage. And then we want to see how is this linear regression related to the parameter estimation procedure that we have gone through the last two lectures. So that's part one. And then I want to link the classifier developed by the linear regression and the classifier developed by the Bayesian decision approach. So we want to see here it will be at the estimation level, and here it will be at the classification level. And at the classification level, what are the similarities and what are the differences? Okay, so to start with, let me talk about linear regression for a while. Okay, now linear regression, if we want to put it under the classification problem, then it belongs to the class of discriminative method because I really do not have any model. I do not have a Gaussian model. I do not have a Poisson model. I just don't have any model for the linear regression. What you do is that you set up a linear system of equations, and then here is your data matrix, and then here is your parameter, and then you set the equality and you minimize the loss function, and you get some solution, right? So that you really do not have a Gaussian model, things like that. In the beginning of this course, when we introduce linear regression, we know that it is for curve fitting. So I give you data points and find a line to fit the data. But we can also do the same thing for fitting a classifier. And the way to do this is the following. You want to construct a hypothesis function. A hypothesis function is defined as a function that takes two states, +1 or -1, when the discriminant is bigger than 0, when the discriminant is less than 0, right? And so we know by now that a discriminant function is nothing but just a W transpose X plus W0. So you have a strict line, and then you have an offset, your slope. That W and W0 can be obtained using your Gaussian model, which is linked by the means, is linked by the covariance matrices, etc., etc. Now, suppose then the W and W0, for now, it is an unknown parameter. I just know that there is a form of the discriminant function, like the Gaussian case. I know there's a form. I don't know the exact vector W. I don't know the exact value W0. I don't know them, okay? But I know this form. So what I want is that I want to put this form into the equation here, and then I still want to evaluate whether this discriminant function will be bigger than 0 or less than 0. If yes, I put a +1. No, I put a -1. All right, so that is my hypothesis. So what should I do? Well, I can just look at the data, and then I try to fit a straight line through the data, and then afterwards I'm going to put a sort of threshold. Okay, once my value is above 0 or 0.5, I'm going to set it to +1. Otherwise, it will be 0. Right? So I will still fit a straight line through the data, and then I'll put a threshold to get to this hypothesis function. So here is what we do in the linear regression for classification. Okay. Now, normally you don't do linear regression for classification, but we can still make linear regression to do classification. So how do we do? Well, you look at these data points. So here we have a set of yellow dots, and then we have a set of blue dots. Okay. And then the yellow dots and blue dots, they are living on the two sides of this x-axis. The blue dots, they all have the same y value of +1. The yellow dots, they all have the same y value -1. Okay? Now, you do not have a value of 1.2. You don't have a value of 0.5. You don't have that kind of value because by classification, they are labeled, right? It's supervised learning. So you do have access to the true label. They're either +1 or -1. Now, the x locations are different for data points, okay? Because this could be the temperature, and then you say that above certain number there will be a threshold, below certain number you have another value. Okay, so this x number will change for different data points. However, the y values, they will stay the same. These are your data points, and then let's pretend that I really want to fit a straight line to all these data points. Now, don't question me how you can fit the data line. Well, I can always treat these as data points, okay? Just be agnostic to where the data points they live, okay? Just forget about that they're living on this surface. They're just data points, and then they are living in this two-dimensional space. I can find a line to fit them. It could be a very crappy line, but I can still find a line to fit them. And so I'm going to fit an orange line through all these yellow dots and also these blue dots. I can do that. I can solve the least squares equation. I can solve that minimization. I can put regularization. I can do whatever I want, as we have learned in the first few lectures. We can do that, and then we find a line. Once we find the line, you set a threshold. What is the threshold? In this case, it will be a midpoint between +1 and -1. So that will give you this staircase function. The orange line is your discriminant function. It's a G function. G equals to W transpose X plus W0. It is the legitimate discriminant function. It's a linear function. It's a straight line. Okay, it has a slope. Now, the staircase function is what we call the hypothesis function. It's the discriminative function. Is taking your discriminant, okay, and then you put a sign, and then you tell whether it's +1 or -1. Right? So that completes the picture of, look, I want to first compute the discriminant function, and then I want to calculate the hypothesis. Okay. In the Bayesian case, this is defined by your what? This is defined by your mean vector, your covariance matrices, and then +1, -1, and you just check whether there's a positive or negative. You do the exact same thing in Bayesian case. Okay. Here is no different. You also do this. It's just that you're not using the mean, you're not using the covariance. There's nothing called mean covariance in this problem setting. Okay. However, you can still find this discriminant function, this G function. All right, so let's recall our memory of how do we do the linear regression. So we define a loss function. This is your discriminant function. You call it G, and then you have a bunch of losses. You sum them up. Then you define this square loss, and then you plug in the definition of this G, which is your linear equation. So remember that this G is W transpose X plus W0. So that's your linear function. You plug it in, you have this square function, and then you sum them up. And that's just the same as solving this system of linear equations. Okay, so this is exactly your linear regression model. And if I want to be more compact in my notation, I'm just solving this minimization over A times theta minus Y, something that we have learned before. Okay, so I can do that. And to solve this problem, we have already gone through this slide. We know that we can take the derivative of this matrix equation set it to 0, then you get a solution is given by this pseudo-inverse. We learned that already, okay? So you find a solution. Now, the interesting thing is about the geometry. When you are not solving it using the closed form, let's pretend that you have a very big matrix system, and then you want to use gradient descent to solve the problem. And so what you're doing is that you first draw all these contours. This is the hidden contour, invisible contour that you don't have access to. And then you start with an initial guess of theta 1. And then at every step, you make a step forward according to the gradient direction. So that's the gradient descent algorithm. Now, the interesting thing goes to the left-hand side of this slide, which is a pictorial illustration of what's happening to your decision boundary as you make progress in this contour map. So on this contour map, you have all these thetas. These thetas, they are the model parameters. They define the slope. They define the y-intercept. Right? If you forget it, the theta, they're here. These are the thetas, and the thetas, they are really the W's and the W zeros. Okay, so they're the model parameters. If I change a theta, that means I'm changing the slope of my straight line, or I'm changing the y-intercept of my straight line. Okay, so suppose you have a set of blue dots, and then you have a set of red dots, and you start with theta 1. Okay, theta 1 is here. This is your theta 1. Okay, now it can be extremely bad because you randomly initialize somewhere, and this line has certain slope, it has certain y-intercept. You put it there, and then it doesn't really classify the thing well. Okay, it's a classifier, it's just not classify the thing well because you have not minimized your loss function yet. And so now you make another step, you go to theta 2, so then you have this gray dotted line. It's a little bit better, right? It's a little bit better. Then you move to theta 3, it's this the dotted line, and so it's getting better. And eventually go to the minimum point, and this is a cartoon illustration, and just to show you that, hey, okay, when you are at theta 4, you get this black dotted line, and if that happens, then you have a really, really good classifier. Okay, so the evolution of this gradient descent algorithm has a consequence to your separating hyperplane. As you have more iterations, and suppose this is your step size is well chosen, then at every iteration, you should be able to see an improved training loss. And by improved training loss, I mean that every step you make, your training loss has to go down. Okay? So that's the bottom line of the gradient descent algorithm. When you move along this contour, your decision boundary actually changes. This is somewhat different from the Bayesian approach. The Bayesian approach says that, look, this is the mean, this is the covariance. I will just draw my line there, done. Okay, there's nothing called gradient descent. There's no iteration involved at all. All right. So, but in a linear regression type of problem, if you're large scale, what you do, well, you actually go through this iterative process. Bayesian, you look at the mean, you look at the variance, boom, this is the equation, and this is the separating hyperplane. So there's a difference here. Okay, that's actually a fundamental difference between generative model versus discriminative model. A discriminative model says that I usually need to solve this optimization through iterations. Generative model says that I spend most of my time calculating the model parameters. Once it's done, you can draw the line. All right. Now, how do we link the linear regression with the model parameter estimation part? Okay, so there are the two linkages I want to bring up today. One is with the estimation, the other one is with the classification. So let's first talk about something closer to us, is the maximum likelihood. We just learned 2 lectures ago. How do you visualize this linear regression from the point of view of maximum likelihood? If you look at the equation, what linear regression is really solving is this. You put a 2-norm square between a theta and y, and you want to minimize. That's the linear regression. Now, I can expand this equation to this sum of the square terms, And all these ANs, they are just the columns of the A matrix. Now, normally we go backward, right? We say that, okay, here's the data point, and then what is the compact form of expressing that? Now, I'm going to reverse direction. I start with this very compact form. I try to expand it to this equation here. All right, then what? Well, then you look at this equation. This is minimization over sum of square. I can always put a minus sign in, and then I can put an exponential there, because this function is just monotonically decreasing. And so I would turn the mean to the max. By doing this, my minimizer is not changed, because my function, this exponential of minus whatever, that function is decreasing. Okay? It's monotonically decreasing. It won't change the optimizer. The optimizer is theta. So if I have a minimum for this one, the same minimizer would be the maximizer for this equation. I can do that. Okay? Now, what is this? This is nothing but a Gaussian PDF, isn't it? Okay, how do I see that? Well, this is exponential of minus something. I can always put a constant here, because the constant has nothing to do with your theta. I can put a constant, and then I can pull the summation outside the expectation by putting a product. Then it will just become a product of all these individual PDFs for data points ANs. It's just a Gaussian, right? It's a product of a lot of Gaussians on each individual data points. And so if you look at this problem, what is it? This is maximum likelihood estimation. You are putting down the likelihood function. In our case, it will be Gaussian. And then if you solve this maximum likelihood problem, it is exactly the same as if you're solving the linear regression problem. Okay? There's no approximation involved. It's exactly the same. Now you ask, then what is the difference then? Well, in linear regression, you do not have that kind of model. Okay? So here, when you solve this problem, you don't know that underlying there is a Gaussian. You can always write into this form. Okay? You can solve this maximum likelihood problem. By solving this problem, implicitly you're assuming a Gaussian. It could be that the underlying distribution is something else. It's not a Gaussian, and so that means you're solving a wrong problem. Okay? Now, they are the same if the theta, the A's, and the Y's, they are really following a Gaussian distribution, then your linear regression is solving the perfect problem. When your A, theta, Y, they are not following a Gaussian distribution, you are solving a Gaussian problem, but the underlying distribution is not necessarily Gaussian, and so even if you get a solution, you're solving a wrong problem. Okay? You can still get something, but it's just that you're not getting the thing that you want. So I want to make a comment here. This linear regression is assuming a thing that the underlying distribution is IID Gaussian with variance sigma square. That's the assumption that if you solve this linear regression, you want to link this maximum likelihood and also the linear regression. Under this condition, then these two are exactly the same. Okay? If this condition is violated, you will still get something, but then the something that you get is not going to maximize the likelihood of the underlying distribution. You're only maximizing the likelihood of your choice of model, which is a Gaussian. Okay? So that difference has to be very clear. Okay. Now, what if I also want to put a prior distribution using the Maximum-a-Posteriori approach? You're welcome to do so. You just put a prior distribution on theta in this form. Okay, it would be exponential of minus rho times rho of theta divided by beta. So rho of theta is just some function. Okay, so let's assume that your prior takes this form. Then you can try to put this equation into here. Then it would be a likelihood times a prior. That will give you the Maximum-a-Posteriori estimation. Now, you can simplify the exponentials by just putting a negative log. So this argmax problem becomes argmean. And then you have this 1 over beta times rho of theta coming out. Then what? Well, then you can absorb this 1 over 2 sigma square going to here. and then define a lambda, where lambda is just 2 sigma squared divided by beta, then you have this equation. Now, what is this equation? This is linear regression with a regularization. See that? Okay, linear regression with regularization. And therefore, this maximum-a-posteriori estimation is literally just linear regression with a regularization. What is the underlying model? Well, what is the model that you're assuming? Not the underlying model. Okay, what is the model that you're assuming? You're assuming a Gaussian model for A, theta, and Y. And what is the model that you're assuming for the prior? You're assuming this exponential of minus a rho. Okay, these are the model that you assume. It is not necessarily the true model underlying, but you are getting something out of this. Okay, so this rho function is called the regularization function. And now we can put in your favorite regularizations, like what? Like the ridge regression that we have learned. You can put the theta square 2 norm. What is the corresponding prior? You can go all the way back. Okay, so you can say that let's assume that your rho of theta is theta 2 norm square, and you assume that beta is 2 sigma naught square. You put this in, then your map estimation becomes this. You have likelihood times your prior, which is this prior. You take a negative log, then you have this term coming out, and this is exactly just a theta minus y 2 norm square plus your regularizer. Right? So this shows you that if you choose a Gaussian prior, then your map estimation is the ridge regression. And then at this point, you can replace what? You can replace the 2 norm square by 1 norm. You will get the lasso regression. That will correspond to not a Gaussian prior, but a two-sided exponential prior. So you will get that. Okay, so now we have linked two things, right? The linear regression that we have learned a long time ago, and also the maximum likelihood estimation, and also the maximum-a-posteriori estimation. And it's actually doing exactly the same thing. The only difference is the underlying model versus the model that you choose to estimate the parameter. Okay, so if the two exactly match, then your linear regression is doing the maximum likelihood. Otherwise, you're solving something, the likelihood that the maximum likelihood estimate you get is the likelihood of something, but not necessarily the underlying true model. Okay. Any questions so far? Yes.
So I can see from the linear regression to when you're talking in the previous 2 classes, you should do some math and add the term sigma into it. And I know it does nothing to do with the selection of beta value. I just want to ask, like, what kind of benefit can it generate if you link this to the other one? So what's the meaning of linking this two together? And by adding up those sigma values, how can we pick up the sigma value which is meaningful, or is that something given by the question already?
So you're asking what is the benefit of knowing this? Okay, does it help us to solve the problem better? The answer is this is unclear. All right. The reason is that even by knowing the linkage, okay, you do not gain additional insight of how do you pick the parameter. Okay. However, what you do know is that by doing the linear regression, there is an equivalent form in doing the maximum likelihood estimation. Okay, so that is the linkage that I don't want you to just miss. Okay, because in a lot of problems beyond what we are talking about here, you sort of see that there is a coupling between the optimization literature and also the probability literature. Okay, so one is more towards the machine learning side. They all embraces the Bayesian beauty and so on. And the other one is just strictly forbidden all these Bayesian analysis. They take the optimization point of view. Here's my objective function, and here's my regularization function, and here's my solution, convergence, etc. The other one would say that here is a model, here is another prior model, and then here will give you the solution. Okay, and so the benefit will come to your problem when you try to solve a problem in one way. You say that okay, I'm using the optimization approach and I get the solution. Can you give me some interpretation of how the solution will look like? Okay. Then you go to the probabilistic analysis, like with the maximum-a-posteriori, that it says, look, perhaps your underlying model indeed fulfills this Gaussian distribution, and the prior that you choose indeed follows this double-sided exponential distribution, and so it has certain sparsity implication over there. Now what? Well, now if I want to proceed further, I can first of all actually check whether my choice of this 2-norm square in my optimization actually has a physical meaning. So I can look at the statistics of my measured data and see if it indeed follows a Gaussian distribution. And then you do an experiment, you find out, oh, by the way, it doesn't follow a Gaussian distribution. Then you know that your optimization approach is wrong. You shouldn't put a 2-norm square in your objective function. Right? So the two perspectives is helping you, depending on which side you are at. Right? So I'm giving you an example that you are from the optimization side, and then you want to get some interpretation of your results. Then you can go to the probabilistic side, and then you can draw some conclusion that indeed my measurements, my data points, they fulfill the Gaussian statistics. And therefore I can justify that my optimization problem is a right problem. Okay. Now, the vice versa is also interesting. You start with all these beautiful models. Okay. And then you say that, no, right, this is a non-Gaussian model, and it fits really, really well with my data. And I have chosen this prior according to my 20 years of experience. Okay. I found that. Okay. And I try to solve the problem. And you run into trouble by solving the map problem. Because why? Because it's not optimizable. Okay. The function is non-convex and it's just too complicated. Then what do? Well, then you look at the optimization literature and you say, okay, these guys saying that the convex optimization helps. So let me try to use some of their tools. And so how do I do that? Okay, I'm going to find the closest convex relaxation to my problem and then find that out, and if it works, and I go back and I verify, indeed, I'm using this kind of distribution, and it kind of makes sense to my problem, right? So the interaction between these two perspectives is more valuable than the computational benefit, right? The computational, I don't see any benefit over here. That if I know, if I have this expression, do I get a better estimate of my beta? That is not the purpose of the discussion here.
And another small one is a sigma selection going to affect anything of your calculation result, or that just the same value, you know it, you know?
Okay, so the question is, how do I choose this beta, or how do I choose this sigma? Okay, so this sigma, the sigma here is measured the amount of noise that you are encountering in this measurement. Okay, so let's say you have this is your x, and then these are your data points. You are saying that all these error they have a Gaussian distribution with a variance sigma square. Okay, so that can be inferred from your data set. Okay, or and that could be a number that you can just put it in. Okay, at the end of the day, what you really care is this number lambda. Lambda would be a ratio of sigma square and beta. And normally you don't choose sigma square, you don't choose beta, you just try and error for different lambdas. Okay. But if you adopt the maximum likelihood point of view, you do first look at the data set, and then you do find out what sigma would match, and then you do find out what kind of beta it would be a good prior according to a 20 years experience. That can define the lambda. Alright, but that, I wouldn't pay too much attention here because, normally you don't have the 20-year experience of choosing the beta, and then you don't really have a way to make sure that this is Gaussian with sigma square. Okay? So at the end of the day, when you sit in front of the computer, you still calculate a bunch of lambdas to try and error.